Hi, in this presentation, I'm going to continue with what I did in the previous presentation on Jacobians. So, I'm going to work out a few more problems pertaining to Jacobians and its properties and their properties. Sorry. So, we will start with this problem today. So, we are given that x and y are functions of r and theta, and in this particular problem we are told to find j, which is dou of x comma y by dou of r comma theta, and j dash, which is dou of r comma theta by dou of x comma y. And further we are told to verify that j into j dash is 1. So this is exactly what we are supposed to do in this particular problem. So to begin with, we will straight away start the expression for j, which is given as dou of x comma y by dou of r comma theta. Now, according to the definition of Jacobians, this will be dou x by dou r, dou x by dou theta in the first row of the determinant, and the second row would be dou y by dou r, and then dou y by dou theta. Right? So, what are these expressions? Now, because x is r cos theta, dou x by dou r is simply going to be cos theta, and dou x by dou theta will be minus r sin theta. So, if you are good at partial differentiation, finding these is actually pretty good, pretty simple. Now, dou y by dou r is sin theta, and dou y by dou theta would be r cos theta. Right? Now, this is what is the expression. Now, you can straight away take out r common from the second column and then expand this, or straight away expand this. So you will see that easily the value of j would be r upon simplification. Okay, so this answers the first part of the question, where we are told to find out j as such. So we got j. Now we'll have to find out j dash, but for that to be done, if you remember, because x and y are given in terms of r and theta, for us to obtain j dash, which is dou of r comma theta by dou of x comma y, we'll have to try to rewrite r and theta in terms of x and y. And first of all, that is definitely possible because the value of j is r, which is generally not equal to 0, because r is just a variable, so it need not be 0 at all. Right? So now we should be able to find out j dash, because j is not 0, and for that to be done, as I said, we have to express r and theta in terms of x and y, and that is actually pretty simple as long as you know as to what these are. If you can recall, this is basically the relation between the two-dimensional variables x and y, right, in terms of r and theta, again as a set of two-dimensional variables but in polar coordinate system. So this gives us a connection between the Cartesian variables and the polar variables, right? So if you can recall, then it is very easy to see that if x is r cos theta and y is r sin theta, x is r cos theta and y is r sin theta, then squaring and adding will give you r to be equal to root of x square plus y square, and dividing one expression by the other is going to give you theta as tan inverse of y by x. So this is what is going to be the expression for r, and this is going to be the expression for theta in terms of x and y. Without these two expressions, you will not be able to proceed further to find j dash. Now because now we got r and theta in terms of x and y, we can proceed to find out the expression for j dash. First of all, j dash as given is dou of r comma theta by dou of x comma y, right? And this is determinant of dou r by dou x, dou r by dou y. So that will be the first row, and for the second row we will get it as dou theta by dou x, and then dou theta by dou y, right? So this is what is going to be j dash. Now to find out dou r by dou x, we'll have to use this expression. So because r is root of x square plus y square, dou r by dou x would be 1 by root x square plus y, 2 root x square plus y square into differentiation of x square plus y square with respect to x partial is going to be 2x. So in that 2 will get cancelled off, and you will be left with x by root of x square plus y square. Okay. Similarly, you will get dou r by dou y as y by root x square plus y square. You can check it out later on as to how exactly you will get this as. Okay. Now coming to the second row, we find for you to find dou theta by dou x, you have to differentiate this theta with respect to x. So first of all, tan inverse y by x upon differentiation will give you 1 by 1 plus y by x the whole square. Correct? And now when you differentiate y by x with respect to x, that will give you minus y by x square. Correct? So this is what you will get as dou theta by dou x. So I will write simplified version of this. In this, if you take the LCM here, this will give you x square plus y square, and that x square will get cancelled off with this x square. So you will be finally left with minus y by x square plus y square, right? That is dou theta by dou x. And when you go for dou theta by dou y, once again y by x the whole square, but instead of minus y by x square, you get a 1 by x here, because differentiation of y is 1 and 1 by x will remain as it is. That when simplified will give you this as x by x square plus y square, x square plus. Okay, so this is what is j dash. Okay, now so this before is what is j dash. Expanding now this determinant, before I would like to take out and y square common from the row, and that will give me effectively x square plus y square to the power 3 by 2, right? And the rest would be simply determinant of x, y minus y, and this would be x. Correct? Now expanding this now will give you x square plus y square, and you will be left with finally 1 by root x plus y square. Okay, so this is what is going to be j dash. Now that completes answering the second part of the question here. So in the second part we were supposed to find j dash, and now there is one more bit in the question where we are supposed to show that j into j dash is going to be 1. So now we will begin with the expression for j into j dash. So we will consider j into j dash. If you remember, j is r as we got here. Correct. So this is r into r into j dash. We got it just now. that has to be 1. So 1 by, sorry, not just 1 by root x square plus y square. Now the rest is to show that this is 1. So if you know root of x square as we saw earlier is nothing but r. So obviously r into 1 by r is going to be 1. So this completes answering the third and the final part of the question. And that's exactly how we are going to solve this problem. Okay. I hope you have followed this part. Now we'll take up little similar problem as the next one. Yeah. This problem is about showing that u, v, and w are functionally independent using Jacobians. Of course, there is another bit where we'll have to find out the inverse J dash, and of course we'll also have to show that J dash is going to be 1. Now, before all that, first of all, what do you mean by functional independence? If you remember, in the previous session we have discussed this. So when we say functional independence, it means to say that the three variables, as you can see here. Of course, it could be two variables or three variables or any number of variables. In this problem, we have u, v, and w. So when you say that they are functionally independent, it means that you will not be able to express u in terms of v and w, or v in terms of u and w, or w in terms of u and v. That's exactly what we mean by function independence. And checking whether they are function independent as such is tedious, and that is where the role of Jacobians has to be understood. So to show that the functions u, v, and w are functionally independent, you just have to show that the value of the Jacobian is non-zero. As long as you can show that, you can straight away claim that the three variables u, v, and w functions are functionally independent. Okay. So what we are supposed to do now is we'll just have to show that the value of j. Yeah, first of all, what is j here? J is dou of. As you can see, the dependent variables are u, v, and w. And the corresponding independent variables are x, y, and z. So now u by dou of x is Jacobian, and we are supposed to show that this is not 0 for these to be functionally independent. So without spending too much of time, I'm going to straight away write the expressions for these, because by now I hope you know what each of these is. Okay, first will be dou u by dou x. Okay? What is dou u by dou x from this? Because u is x plus y plus z, dou u by dou x will simply be 1 plus 0 plus 0. Right? Now the next would be dou u by dou y, and that is again 1, obviously, and dou u by dou z is also going to be 1 for the same reason. Okay, so the first row would be 1 everywhere. Okay, so 1, 1, and 1 is what makes the first row. Similarly, when we go for the second row, first element would be dou v by dou x, and because v contains only y and z, dou v by dou x would simply be 0, right? And then dou v by dou y would be 1, and dou v by dou z would be again. And the third row would be dou w by dou x, dou w by dou y, and dou w by dou z. Now because w is simply z, dou w by dou x would be 0, dou w by dou y also 0, and dou w by dou z would be 1. And I think we all know that if you have triangle matrix or lower triangle matrix or diagonal matrix, the value of the determinant is nothing but the product of the diagonal elements. So this would give you the value of j as 1. Right? And very importantly, now as you can see in the question, there is no mention about finding the Jacobian, but of course we are supposed to show that u, v, and w are functionally independent. That is where the role of Jacobian comes. So we will now say that j is not equal to 0, right? So the value of j is j is not equal to 0 right? So because j is not equal to 0, I would say that the variables u, v and w q and w are functionally independent. So because j is not 0, u and w are functionally independent. Okay. Now what next? So this answers the first question here. Remember, such questions can easily be asked for 5 marks. In fact, such is the nature of such these questions that you can easily answer each of these parts and accordingly get 5 marks pretty comfortably. Okay, so now we have shown that u, v and w are functionally independent. Now what next? We are supposed to find the inverse Jacobian j dash. Now when it comes to three variables in terms of three variables, it's not very trivial to find the inverse Jacobian, because if you have to find the inverse Jacobian j dash, you will have to express, see, first of all, in this problem, u, v and w are given in terms of x, y and z, correct? So this is exactly what is given here. But for you to find the inverse Jacobian, you will have to go the other way around. You will have to express x, y and z you will have to express x, y and z in terms of u, v and w, right? So this is exactly what we are supposed to do. And for that to be done, you will have to observe carefully and see as to what u, v and w are in terms of x, y and z. If you can see that and think a little, things are going to be pretty easy to proceed further. Okay, so now this is exactly what is given. U is x plus y plus z, v is y plus z and w is z. So now I'll have to go the other way around. So when I try going the other way around, first of all, because w is z, I can easily say that z is nothing but w, correct? And because z is w, from this relation we see that y is, sorry, v minus z. Okay, and because z is nothing but w, I can replace z by w and I can see that y is v minus w, correct? So that has given me z in terms of w and y in terms of v and w, and the rest is about finding x. And coming to the first expression, we see that x is nothing but u minus of y plus z, and because y plus z is nothing but v, I can say that x is nothing but u minus v. Okay, so I would first write this in particular order. So x is u minus v, y is v minus w, and z is w is we have got is what we have got here. Correct. Now have we got what we wanted? Remember, for you to find the inverse Jacobian, you have to explicitly express x, y and z in terms of u and w. What I am trying to tell you here is that suppose you come to this expression. One second. There is some problem with the system because of which we're getting stuck with the expressions. Yeah, so as you can see here, when you look at this expression, can I say that this is the required expression, y equals v minus z, or x equals u minus of y plus z? Of course I've got x on the left hand side and y on the left hand side here, but this is not complete because I have v and z on the right hand side. I should not have, see, when I want x, y and z in terms of u, v and w, I should not be writing y in terms of x and z. So this is not complete because y is in terms of z. Same way x is in terms of y and z. So this is not complete. But now this part is okay because y is purely in terms of v and w and not in terms of x and z. Similarly, x is in terms of u and v and not in terms of y and z. Okay, so this is a complete transformation. X equals u minus v, y equals v minus w, and z equals w. Now I think we can proceed further to find j dash. Okay, so j dash. First of all, what is j dash? This is dou of x comma y comma z by dou of u comma v comma w. Now here you'll have to be a little careful when you write the expressions. So what is the first term? Dou x by dou u. So what is dou x by dou u? It is simply 1. Correct? Because this will become 0 when you differentiate this with respect to u. And what is the second term? Dou x by dou v. Now what will be dou v? This term will be 0 because we have minus v. The second term will be minus 1. Okay? Dou x by dou w, because it does not contain a w term at all, this will simply be 0. Okay, so the first row would be 1, minus 1 and 0. Similarly, the second row, dou y by dou u, because y does not contain a u, this will be 0, and dou y by dou v will be 1, dou y by dou w would be minus 1. And finally, dou z by dou u, does not contain u, and dou u will be 0, dou z by dou v 0, and dou z by dou w would be 1. And once again, this is an upper triangular matrix, and this of course will give me the value of j dash as 1. In fact, you should know that j dash is supposed to be 1 because j is 1. Why? It is because effectively the product of j and j dash is supposed to be 1. Correct? So j and j dash should be 1. So if j is 1, of course j dash also should be 1. So now the next part is just to show that j into j dash is 1. So it is just to show very trivial, at least in this problem, because j is 1 and j dash is j into j dash is 1. So it is very trivial, at least in this problem, because j is 1 and j dash is 1. So j into j dash is 1, of course. So this completes solving this question. Right? Fine. I hope you have followed this part as well. Now it's the time to go to the next question. Yeah, this is somewhat different from the previous questions. So first we'll read the question carefully. Show that dou of u comma v comma w by dou of x comma y comma z is 0, where u, v and w are given as here. So of course this is nothing but j as we know. So first thing, yeah, of course there is another bit in the question, but we'll try to address that part later. So we'll try to answer the first part straight away. Okay, so first of all, we'll begin with dou of u comma v comma w by dou of x comma y comma z. Okay, so what is this? Dou u by dou x is the first term. Dou u by dou x is of course 1. Dou u by dou y is also 1. And dou u by dou z is 1. I've chosen simple problems at least here so that I can proceed further easily. Okay, so next row, dou v by dou x. What is dou v by dou x? As you can see here, there is no x term at all in v, so this will be 0. Okay, what is dou v by dou y? Dou v by dou y would be 4y from this, and then this is 4z. Correct? Right. And when you go for dou v by dou z, what will be dou v by dou z? Once again, this would be, let me show 1 minute. Probably I should have written this a little far from this expression as such. Yeah, so this is 1, and this will again be 4z plus 4y if you look at it carefully. Correct? And when you go for dou w by dou x, dou w by dou x would be e power x. Correct? And dou w by dou y would be 0, and dou w by dou z would again be 0. Am I right? Right? Yeah. So this is exactly what I have now. Now, before expanding, probably it is better for me to take out e power x common. E power x is common here, correct? And then 4y plus 4z is common from the second row. I'll take that common. Okay. And what am I left with? I have a 1, 1 and a 1 in the first row. And now I have a 1, 1 as the second and third row elements, sorry, second and third column elements of the second row, and I have a 1 in the first row, sorry, third row first column of this determinant as such. And what's the value of this? Of course, we are supposed to show that the value of this is 0, so you should be able to show that this is 0 very easily. In fact, you can nicely use the properties of determinants to show that this is 0. For example, as you can see here, if you perform R2, again, of course you can straight away expand and do this also, but I want you to recall some stuff that you have learned in your previous classes. So if you perform R2 change to R2 plus R3, you see that you get a 1 here, so this will be 1, 1 and 1. Correct? And once you get a 1, 1 and 1, these two rows will be identical, and that will straight away tell you that the value of the Jacobian is, the value of the determinant is 0, so consequently the value of the Jacobian is 0. Right? If you still are confused, you can try expanding this further, and you will see that the value of the Jacobian is 0 even by the usual expansion of this. Okay, so anyway, now we have got this to be 0, but that's not the only part of the question to be answered. So of course we have shown that this is 0. But now look at this. Further, establish a relation between u, v and w is what is being asked. Now, how can you establish a relation between u, v and w? If you recall, I think in the previous one or in the other one, I think I've told you, no, I think it is in the previous question itself. I've told you as to what we mean by functional independence. What do you mean by functional independence? You say that two or three functions are functionally independent if the value of j is not equal to 0. Accordingly, if the value of the Jacobian is 0, then we see that the variables are functionally dependent. Okay? So now, because we have got the value of the Jacobian as 0, we now see that u, v and w are going to be functionally dependent. And what do you mean by functional dependence? It means that you will be able to establish a relation between u, v and w, or you can try to write u in terms of v and w, or v in terms of u and w, or w in terms of u and v. Now how do we do that? Of course, it's not very easy to do that generally, but if you practice solving a good number of problems, it might be easier for you to observe and see as to what could be the possible relation. Of course, I've chosen a simple problem here to make you understand as to how to connect u, v and w. See this? These are u, v and w. So if you observe carefully, you see that I would put it this way itself here. By observation, you are supposed to observe and see this. So what happens here? If you look at this, see, you have u to be x plus y plus z. And if you look at v, in this, if you take 2 common, what will be v? V would be 2 into, yes, it will be y plus z whole square. Correct? Y square plus z square plus 2yz is y plus z the whole square. Okay, so v is this, and w is e power x, and u is of course x plus y plus z. So putting these three together will give you, yeah, can you guess the relation? See, y plus z can be replaced by root of v by 2 here. Okay, so I'll take y plus z to be root of v by 2, correct? And what am I left with? I'm left with x, and that x could be written using this relation. Now what is x then? If w is e power x, x is going to be simply log of w. So u is going to be root of v by 2 plus log w, and this is exactly what we mean by a relation between u, v and w. And this can happen only when the value of the Jacobian is 0, is what you have to understand. Okay, so remember, this is going to happen specifically when j is going to be 0. As I said, it's not very trivial finding this relation. So only if you practice a good number of problems solving, you will be able to find out or guess as to what could be the possible relation. So practice well so that things are going to be good for you. Okay, so this is another problem that I want to discuss, that I wanted to discuss with you. I would like to wind up this section with just one more problem. I'm not going to solve the whole problem for you. The next one, I'm going to just tell you as to what exactly has to be done initially, and the rest I'm going to leave it to you. What's the question here? We are given x and y in terms of r and t, right? So x and y are given in terms of r and t. Okay, what next? X and y are in terms of r and t, and further if you look at it, r and t are given in terms of u and v. So r is in terms of u and R is also in terms of V. Similarly, T is in terms of U and T is in terms of V. So if you look at this finally, you see that the final dependent variables are X and Y, and the final independent variables are U and V. And because this is the final relation between the given these variables, we are supposed to be able to find out j of x comma y with respect to u comma v. But the problem is that x and y are not explicitly given in terms of u and v. Instead, x and y are given in terms of r and t, and r and t are given in terms of u and v. And that is where you will have to use concept of composite Jacobians. This I have told you in the previous class. We will recall the expression for this. So if you remember, if you want j of x comma y with respect to u comma v, this is going to be j of x comma y with respect to r comma t, and then this multiplied with j of r comma t with respect to u comma v. So this is very much similar to the chain rule that we have in differentiation. Okay, so for you to find out j of x comma y with respect to u comma v, first find out j of x comma y with respect to r comma t. Can you find that? Of course yes, because x and y are given in terms of r and t. So that will help you to find out j of x comma y with respect to r comma t, and then find out j of r comma t with respect to u comma v. How do we do this? This will be done using this expression, these expressions. So you can find this. Once you got this and this, the rest would be to multiply the two and write that as j of x comma y with respect to u comma v. Of course, in the final expression, everything should be written in terms of u and v effectively, because the final independent variables are u and v. Okay, so this, as I said, will be finally a function of u and v, remember. So I'm going to leave the rest of solving this problem with you, because you can easily find this and this. So try this out and finally express everything in terms of u and v. So this is how you are supposed to deal with problems pertaining to composite Jacobians. Okay, so these are different questions pertaining to Jacobians that you should be able to answer. So practice some more questions pertaining to Jacobians, and if you can, then things are going to be much easier for you in the examination, is what I can say. So with this, I'm going to end with this session. So as always, study well for the examination, and feel free to ask me questions pertaining to this, either in the uh, Telegram group or on YouTube itself, or you can message me personally as well. Okay, so study well, see you soon.